the function, which is x raised to some even power, is going to always look the same. So parabola y is equal to x to the second, or if you look at the fourth degree parabola, y is equal to x to the power of 4, are going to have their ends that pointing upwards. In other words, we're going to have so-called even end behavior. I say, what about x to the power of 6? Well, analogously, so if you get even powers of x, they're always going to be in the shape of parabola. So it's kind of hard to say the difference in between the x squared or x fourth or x6. And the key idea is that both ends are pointing up. And similarly to this, we are going to also have odd powers of x, such as a cubic parabola that we already encountered on the test, on the midterm. And its friends, such as a fifth power of x that will also shape pretty much the same way. So both ends will go one up and the other down. So the main idea of this class is to make sure that we can graph those power functions without doing lots of points plot, but just know the shapes of those graphs. So here's on the next page, they're actually discussing cubic parabola and then figure 5 fifths power function. So you can see that indeed these are in the same shape. So also we know that if you put a negative sign in front of your power, the graph is going to flip. So if you put a minus in front of the x to the power of 5, then the graph is going to flip, or people say reflect, through the x-axis. And this be another parabola that has one end pointing up and the other pointing down, but one reflected through the axis. Also, when you working with the, say, fourth power parabola, which is similar to x to the power of 4, you do exact same set of transformations that we do with the x squared. So let's say if they want to subtract 1 from x itself, then the function moves by 1 unit to the right. And also if they multiply by 1/2, then this parabola starts to be wider. So if they multiply by the number smaller than 1, the function expands, people say. And if it's a number less than 1, then function contracts. But the shape of it is still analogous to the original one. So these transformations that happen with a graph turns out are uniform for all of the functions, no matter if you're dealing with the x squared or x cubed like you worked with past test. Now they are moving to other powers of x, and the idea is exact same. So nothing changes if you have a different looking function. For example, if I try to do problem number 27 that wants me to graph y is equal to x plus 1, and now it's raised to the power of 4, well, you still need to deal with the fourth degree parabola, the one that I have here on the left side. And if they added 1 inside the parentheses, the graph had to shift by 1 unit to the left side, right? And you can always double check and see if that really works. So you can put the point with coordinates x equal to -1 and y equal to 0 into the equation. So if I test this and see if 0 is indeed equal to -1 plus 1 raised to the power of 4, then when you calculate the right side, you will get a 0, right, in the parentheses. Raised to the power of 4 is indeed equal to 0, so you can see that, yes, this checks. So this is the standard way to check if you done the graph correctly. So fifth power, like problem number 38 here, that says, what if you decide to multiply by 1/2? What's going to happen with the graph? Well, it's going to expand, right? So it looks like they are talking about 1/2 multiplied by something with x to the power of 5. Well, the fifth degree function with negative and behavior is going to be expanded, so it's going to be like a wider looking parabola. And then I'm going to put a couple of transformations on it, such as a subtract 1 means we shift this graph to the right by 1 unit somehow. So if you have a 1/2 multiplied by x minus 1 in the parentheses to the power of 5. So we just graphed analogous function with x plus 1. So x plus 1 we shift to the left. So if it's x minus 1, then the graph goes by 1 unit to the right direction. And then finally, I will get the answer to the exercise number 38 that also wants me to subtract 2 from the whole thing, which means that I need to bring this graph down, right? And have the white looking fifth power parabola to shift to the level of 2 with negative sign downwards. So the answer for problem number 38 will look like that. So we have a minus here. And you can see the analogy with what we already saw previous sections. So when you have something with the x to the power of 3 or x to the power of 2, or if function has fifth powers, well, it doesn't really make any difference from perspective of graphing, because all you care about is how to do this transformations by how many points to the right or to the left, or sometimes you even flip this so-called polynomial functions. And that's the word they coming up with in this section. They, instead of calling them just functions, they actually use word polynomial. So the key idea for problem like number 41 that says if our zeros of the function zeros are -1, +1, 3, then we have them producing us polynomial with factors that contain these zeros that are being subtracted from variable letter x. So whenever you have these so-called zeros of the function or numbers that make our function equal to 0, then you can actually produce the function by simply multiplying x plus 1, 2 minuses mean plus, right? By x minus 1 and by x plus or x minus 3. And if you actually care to multiply, then product of first two will be x squared minus 1, right? Because when you multiply the two factors, such as x minus 1 by x plus 1, then the product of first terms, x and x, will give you x squared. The product of last terms, plus 1 times minus 1, will give you that -1. And then inside, I get a product of 1 and x, and outside, I get a product of -1 and x, and they will cancel each other out. And then I need to also multiply this with x minus 3. So if you start to distribute, if you multiply x by x, you get x cubed, x squared by x. And then minus 3 times x squared will be minus 3, x to the second power. And then you also distribute -1, so this be minus x and plus 3, just like that. So notice they're talking about the polynomial of degree equal to 3 here, and degree is the largest power of x, and indeed it is 3. So the point of story that if you decided to set this function equal to 0, then we produce this so-called zeros out of every single factor of this polynomial, and there are 3 factors, so there'll be 3 of those zeros. When you have 0, you get a factor, and if you have a factor, it gives us 0. So in exercise number 45, kind of similarly, I can say that since here we have 4 of those zeros, there are -4, -1, 2, and 3, then right away I can get the factors of this polynomial parentheses with those zeros that will be subtracted from our variable letter x. So first we'll have x minus 4, and second we'll have x minus 1, and etc. So I just copy these so-called zeros way they are, and then produce parentheses with x minus those zeros. So I got something that look like that. Now, I don't want to distribute these, distribute these factors one over the other, but you can see since there are 4 of those so-called zeros, then if you take pains to distribute like I did in my previous exercise, you will get the largest power of polynomial equal to 4, and that's actually what we are given in this exercise. So zeros give us factors and factors give us zeros, so this is like a dual procedure. I'd like to see what's going on in the next section, in section 4.3, that continuous graphing. And this section actually works with fractional functions, the ones that have denominator that also contains variable letter x. So notice that whenever you have that x in denominator, then you end up having so-called vertical line as the asymptote. And since 2 makes denominator equal to 0, then this vertical asymptote is going to be 2. So what does vertical asymptote stand for? Well, it's actually invisible line that my function will get closer and closer and closer to, but never touch. So this is very helpful for a graphing. So you can see that both ends of this function, capital R of x, are approaching to this asymptote. So let us try to discover these vertical asymptotes, and I'm going to look at the exercises in section 4.2, the next section. And turns out all we care about is just looking at the denominators of these functions. So if I start with problem number 13 with a function r of x, or I can call it as y, it doesn't really matter. You can always use letter y, that has 4x on the top and x minus 3 on the bottom. Then the main, or the points that I can plug in to my function, will contain everything with exception of number 3, because if I utilize 3 instead of x, then I'm going to end up with something with a 0 in my numerator. So I'm going to plug the 3 in denominator, and whatever the number is on the top, then I'm going to end up dividing this by 0. And this is not what we can do. We don't divide by 0. We can say, Alex, are you sure? Why can't we divide by 0? Well, ask your little friend, the scientific calculator, the one that we already utilized before. Remember, the first choice called Desmos is what I like to use. You can use any calculator whatsoever. And if you try to divide number 12 by 0, you see what happens? The calculator doesn't like it. It's undefined. So turns out that this means that we are not allowed to divide by 0. And this means that we actually going to have so-called vertical asymptote at x equals to 3. It turns out that these functions, they also have horizontal asymptotes. And the way to produce this so-called horizontal asymptote will be to look at the numbers that multiplied by x here and see that 4 is on the top multiplied by x and 1 is on the bottom. So we're going to get y equals to 4. So other asymptote, which is called horizontal, will be x equal to 4. And indeed, if I try to graph this function, let me show you how you can graph it using the technology, using so-called graphing calculator. All you can do is just get into the search engine and type graphing calculator in it. Let me just clean a little bit of this mess. So I'm just gonna type word graphing calculator and it starts to appear. So I click on this graphing calculator that allows you to graph, and our class is all about graphing. So you can see the free graphing calculator, but they're actually pretty expensive. If I, for example, consider a graphing calculator from Texas Instruments that costs over than $100, well, I don't make you to buy one. I just want you to click on the first choice here, and it's going to give you a totally free graphing calculator. And I think that's a good deal. So in order to use it, I just need to click here on the lower left corner where the keyboard is. So I just click on it and get ability to enter my functions in it. So I go ahead and divide 4x by denominator that has x minus 3. And notice that when I entered this 4x over x minus 3, I produced exact same thing that the exercise is asking me. And you can see the red pieces of graph. And in order to see it a little bit better, looks like I need to click on that minus here. In other words, to zoom out. And when I do this, zoom out once or twice, then you can start to see the graph that actually does have these same asymptotes, the horizontal and the vertical one. So you can see that graph is here, one piece of it, right? Approaches to the asymptotes, and on the other side, it's there. So indeed, these asymptotes are very helpful if you decide to graph your function. And one of them is that so-called horizontal asymptote that is passing, looks like, through 0.4, and it is indeed one with equation y is equal to 4. And the other vertical asymptote is here, it's x equal to 3. So we have another asymptote, which is the vertical one, x equal to 3. So this way I can produce various graphs just by utilizing this free calculator. So let me share the link to it with everyone. I think it'd be very useful if you have access to it. So I just put this link to the calculator in the chat. I guess we're lucky that we have access to totally free calculator, right? And we can always utilize it whenever you decide to graph any function. So you can also save it. So if you open it, you can click on this little star. So it'll be saved among your favorites. And those favorites you can always clear if you don't like it. So it becomes less favorite. But I guess for this particular time period, it's a good idea to have this calculator saved so you can always utilize it, right? In fact, I wanted to announce that I will be teaching a next math class called pre-calculus. And that's actually the way that our textbook is called, right? It's also called pre-calculus. I will be teaching it in the summer by Zoom, exact same way that I'm teaching this class. So I'm going to be lecturing on Zoom and giving you tests and quizzes on Zoom. And if you like the way you do in this particular class, well, I think that in the next class in pre-calculus, you'll get the same grade or even better, because I have to use the same book and we're going to go over the same material. So I advise you, if you need to take that pre-calculus class, which is the next one after this, after college algebra, because college algebra is a prerequisite to that pre-calculus, well, then take it in the summer. Don't wait till fall, because over the summertime, it's like 3 months, you might forget quite a few things. In fact, there are students that forget everything and don't remember the stuff. So I'm sure you will easily pass the pre-calculus, because we're going to use the same book and we're going to go over pretty much the same sections. So I'm going to cover same stuff again. I just go a little deeper. You notice that some of the sections say skip, so we're going to actually look at those sections that were skipped, and I'm sure that you will do well on this next class if you do good on this class. And you can always utilize that pre-calculus for transfer, because it always looks good if you took math classes, if you transfer into four-year school, or if you're not sure if you need it or not, well, who knows, in a couple of years, you might change your major to, say, computer science or something like that, and that class will be required to take if you're, say, in a medical school. I think if you go for a medical doctor degree, you have to take and pre-calculus and calculus 1. So think about it. And again, it's a great opportunity. And I teach this class this coming summer semester. You can check the schedule and, well, just register for it, because again, it'd be all in terms of recordings. So if you like to move or visit some other country in the summer, well, you can still have access to it as long as there is an internet there. So I guess that'd be a great class to take, because we're going to use exactly the same book and we're going to cover exactly the same material, pretty much the same. So anyways, let me do some more problems here. Let me do some more graphings. So I'm going to be graphing various functions that have denominators, ratios, and that's why these are called as rational functions. So how about the one that appears in the exercise number 19? So let me try to graph that one. I just want to clean a little bit of this mess. So exercise number 19, as you can see, has denominator who is x to the power of 3 minus 8, right? So let me write this down here. So that denominator is never equal to 0. So x cubed minus 8 is not 0. We already know why, because I do not divide by 0. And that's why we right away declare for our domain that x to the power of 3 minus 8 is not equal to 0. So this means that x to the power of 3 is not equal to 8. And when I cube root both sides of this equation, then I get that x is not equal to number 2. So 2 to the power of 3 is 8. So I'm gonna get this so-called vertical asymptote. X is 2, just like in the previous exercise with denominator x minus 3, we had vertical asymptote x equals to 3. It turns out that to find the horizontal asymptote here, I need to look at the powers of x. And with denominator, I have a bigger power. Denominator is x cubed. So this means that my horizontal asymptote is y is equal to 0 or y-axis. So let me try to make a picture of this particular function using my new friend, the graphing calculator. So I'm going to just move to the next record, or I can just delete the previous one and divide letter x here by x cubed minus x to the power of 3. How do I enter it here? Well, to enter cube, you need to put this a to the power of b symbol. So if I divide by x to the power of 3, and then I have to also go ahead and subtract 2 from that, then we can see the graph that has those two asymptotes. When you say this graph is supposed to be zoomed in a little bit so you can better see the way it looks. So here's the plus, right? I used to zoom out. That's why my picture is kind of needs a little bit of work. And now you can see that indeed this function has two asymptotes, just as we predicted. One asymptote is my vertical line x is equal to 2, so it looks like it approaches upwards to that line and goes along the x-axis. And the other asymptote is the line that has equation y is equal to 0, right? And that's my x-axis. I say, Alex, it makes some kind of wiggle and passes through that point. How do you discover that point? Well, for that matter, you need to learn calculus. We actually discuss finding those so-called maximum points in the calculus classes. So here we don't really talk about it. But what we can also notice that this graph is passing through point 0. So we can see that if I want to find so-called x-axis intercept, all I need is to set my y, or actually this entire fraction, x divided by x to the power of 3 minus 8 equal to 0. And this means that only my numerator, only x is equal to 0, because denominator is never 0. In fact, we just declared that our denominator x cubed minus 8 is not 0, but numerator 0 of numerator gives me that intersection with x-axis. So it is another helpful thing to know, the point of intersection with x-axis. So again, today we are graphing. In fact, in this class, we're gonna be graphing. You already know that, right? So this graphing calculator, I think, is an excellent tool that helps us to double check if you graph this function correctly. So this section turns out, along with the next section, is talking about exact same type of functions. So I can show you the next section that actually deals with this asymptotes and graphings of functions as well. So it turns out that talking about section 2 of chapter 4, I'm also talking about section 3 of chapter 4. You can see exactly the same exercises in both of these sections. So why don't I do another problem here? Let's say a graph, the exercise number 11 that wants us to work with the function that has x squared in denominator. So now I move to the next section because again, problems, as you can see, are the same. They also fractions. So here I have 3 divided by x to the power of 2 minus 4. And I start as usual. I'm going to get so-called domain, which means that x to the power of 2 minus 4 denominator is not equal to 0. So x squared is not equal to number 4, which means that x cannot be 2 or x cannot be negative 2. Notice that negative 2 squared is also 4, right? And that's why I can see there are 2 vertical asymptotes that have equations x equal to minus 2, and the other one has equation x equals to plus 2. So that's the starting point in graphing, just like in the previous exercise when you had x not equal to number 2, we had only one asymptote, x is 2, but in this case, looks like we have 2 asymptotes. So the graphs get a little bit more interesting. Now, there is another asymptote, which is called horizontal. And notice that denominator has bigger power than what we have on the top. In fact, on the top, it's 0 power of x because 0 power of x is 1, right? So we have just a 3, which means the power of x is 0. Since the power of x is bigger on the bottom, then I can say that y equals to 0 is another asymptote. And it's always like that. Whenever you have denominator that dominates, then you get the asymptote, which is called horizontal. So why don't I graph it? So I go back to this new favorite calculator and divide 3. So just enter number 3 by denominator with x squared minus 4. And looks like I should zoom out a little bit to better see this graph. Remember, we had this minus on the right side. So indeed, we deal with 2 vertical asymptotes, and then we also approach to the x-axis. So there is one vertical asymptote, and on the other side, there is another vertical asymptote. And here we are dealing with the graph that looks like that. In fact, notice that this graph is symmetric through y-axis, right? And it's symmetric because I can see only power of 2 or even function. Even power means it's even function, and even functions, they always symmetric with respect to y-axis. So that's kind of nice to know, right? That function is symmetric through y-axis. That's helpful when you want to do a graphing. So looks like these ideas are of having asymptotes is a key part in this sections, in the section 4.2 and 4.3. And my plan for today is to talk about these sections and do graphing. And well, let me just graph another one for you. How about number 17? Another fractional graph. And looking at 17, you probably already see what the asymptote is supposed to be when I have a fraction with denominator, right? So let me get this number 17 here. I write this as a y, which is equal to x to the power of 2 divided by x squared plus x minus 6. So I'm going to graph it without a calculator. And of course, then if you want, you can double check and see if the graph is indeed the same. So I hope now you have access to this graphing calculator, and I think it's a really wonderful tool to utilize. So why don't I right away factor this polynomial, and I factor x squared, the first term as x times x, and then I factor -6 as 3 and -2, right? And then I set this equal to 0. Actually, it's not equal to 0 because my denominator is not equal to 0. So if you want to double check if it's factored correctly, you multiply the inside 3 by x, it's 3x, and on the outside it's -2 times x is -2x. So 3 minus 2 gives you plus 1x, and that's exactly denominator that we have. So I can say that x is not equal to -3, because if I have -3 here, then it makes a 0 for my first factor, for my first parentheses. And analogously, x is not equal to +2. So this means that we actually have a pair of these vertical asymptotes, right? So one of them is 2, and the other of them is -3. So now we have another asymptote to produce, and this will be a quotient of so-called leading coefficients. So y is 1 divided by 1. Notice the powers of x are the same, so I'm getting another asymptote, this so-called horizontal asymptote, with equation y is equal to 1. So I divide those leading coefficients. And I already prepared the asymptotes, so in order to finish up with my graphing, I need to get some points, right? And it turns out that very useful points will be points of intersection with x-axis. X-axis intercepts, or y is equal to 0. That's a definition of points of intersection with x-axis. That's good to know, or to write it down. And when I set y equal to 0, it means that I have to set my numerator only equal to 0. So I say that x squared is equal to 0, or that x is equal to 0. So when I have the point of intersection with my x-axis, then this is going to be a 0. That's the only point that I need to put on this coordinate plane. So now I'm going to graph this function so it approaches to the so-called vertical asymptotes. And then I must put the rest of function in such a way that it approaches to my horizontal asymptote. So I put these arrows, that means that they keep going along the asymptote. And the same thing will be on the other side. So it will be here going upwards and along the asymptote. And if one says, Alex, how do you know that? Maybe it goes like that. Well, it can't, because it will have another intersection with x-axis. And we just found that we have only 0 as the intersection. So we cannot have this function going downwards along the asymptotes, because it will intersect our x-axis, but it is not allowed. So points of intersection with x-axis, I think, are extremely helpful to know, because they give us ideas of how to graph. So today we looked at the graphings of fractional functions, and I'd like to do a little problem to show you another asymptote, and then I will ask you to find the asymptote as well, just the asymptote, because for the quiz, I know you cannot put anything in the any graphs in the chat. So what I can do is just find vertical asymptote only, and I will do problem number 9, and then I will ask you to do the same thing, but for problem number 10. So what's the vertical asymptote for exercise number 9? So I'm not going to graph it, I just find the asymptote, and looks like the main will actually give it to me, right? So we always start by looking at denominator, 2x plus 4, and we declare that it is not equal to 0, right? So 2x is not equal to -4, and this means that x is not equal to -2, right? And vertical asymptote is going to be x is equal to -2. We say, Alex, it's not equal. Well, yes, but that's the asymptote. That's what I found. So you just care about denominator, and that determines so-called vertical asymptote. So let's have a little quiz for today. So how about if you try to do problem number 10? Again, please tell me, what is the vertical asymptote for the exercise 10? And it'd be analogous to the previous problem. You just say what x is equal to, and that will come from your denominator. So just tell me what is vertical asymptote for the exercise 10, and that's our quiz for today. So please put the answer in the chat. Remember, in the Zoom chat, you should have the answer. And after that, well, you can enjoy the rest of Saturday, but don't hurry. Take your time, because you have plenty of time, right? So once you give me the vertical asymptote, then you can go and relax and have a great day and have a very good weekend.
Thank you.